All right, how's everything going? So questions on ODPs?
There's a difference between having your thing in quotes and not having it.
Yes, this is true.
That was one tripping me up.
Okay. Good thing to notice. So today's ODP is the last one for the week, and I'll crank up some more next week. But the one that's posted right now for tomorrow morning is the last one for this week.
For yesterday's ODP, I tried passing the mode for F open as a character instead of just a string,
Oh,
and it didn't like that.
seg fault?
I think it just yelled at me saying I was trying to pass the wrong data type.
Okay. It'll give you a warning, but it should compile, and then it should just puke.
I didn't even check to see if it compiled.
Okay.
It spit out an error at me, so
Yeah.
I had to deal with it.
Okay. Cool. PA4 questions. Got trees under control mostly? Delete's like the last hurdle, right? But if you don't get delete working, don't be too upset over it, because delete's hard, right? It's definitely could be a separate problem in itself, but try to get at least the other pieces working. And if delete doesn't work, right, turn in the other parts that do work. Yeah.
So for free your nodes, could you just go prep first search instead of you just free them as you go down?
Sure. That should work. Yeah, just make sure you do it in the right order, right? So when you pull a node out of the queue, you need to print its data value, you need to push its children into the back of the queue, and then you can free that node afterwards. That should be fine. And when you're done, everything should be free. The queue should be empty. You're doing the queue with a list.
I was talking about just calling the function again on exit, just instead of printing the data at all, just bringing it up.
Yeah.
So, yeah.
That should work. Remember, your queue implementation uses a linked list that probably has a sentinel, so you got to free the sentinel when you're done.
Yeah.
And when you remove from the queue, make sure you're freeing the queue entry. But yeah, that should work. Pretty much any kind of traversal will work as long as you're not freeing something that you still need. So you might want some temporaries or just control the order in which you free them. But that should work. Other questions, comments? Good to go. So I posted a reminder, your service learning project upload is due on Monday by 11. So make sure you turn that in. Download it's the PDF, download the template from Canvas, fill in the sections, cut off the second page of instructions, save it as a PDF, upload it by the due date. If you do that, we will print out a poster version of it and have it available for you for the presentation. So make sure you've at least looked at it and downloaded and understand it before the week's over. All right, good. So I want to revisit longest common subsequence. And I wrote some code the other night. find the longest common subsequence of two strings. So I want to run through this kind of quickly, but as a way of hopefully giving you another view into how this algorithm works. So remember our basic setup. We've got two strings, so something like this. And they don't necessarily have the same number of characters. And our goal is to find some subset of characters from one string that matches a subset from the second string. And these subsequences don't have to be contiguous. We could take this character and this character and this character, okay? But they have to match in the same order. We can't match this character to this, and this character to the first, and this character to the second. So one way to think of this is we're trying to draw lines between matching characters, and we're trying to do it in a way that our lines never cross. Okay, that ensures that we've got the same order. And our question is, what's the longest subsequence of letters that we find in both strings? And so we can think of a function, longest common subsequence, and let's call this first string m and the second string n. And let's say this has little m letters, and this has little n letters. And so we'd like a function that takes the following arguments, takes a string of letters m, the number of letters in that string, a string n and the number of letters in that string, and returns what the length of the longest common subsequence is. And we can write this function recursively based on the following observations. Whatever these two strings might be, suppose they end with the same character. Okay, it doesn't have to be an X, but they end with the same character. Okay, whatever the longest common subsequence is between m and n, that subsequence is also going to end with that same ending character. Because whatever lines we can draw in here to match up characters for characters, we know we can also draw a final line here that matches the last characters. And if we ignore that last character, what we have is a smaller string up here and a smaller string here. And if we were to find the longest subsequence between this shortened string and that shortened string, and then simply add an x to the end of it, that would be the longest subsequence between our original strings m and n. Okay, that's the first key observation. And the observation is the longest common subsequence between these will be the longest common subsequence between these shortened strings plus whatever the last letter is tacked on to the end. And it takes some scratching your head and thinking about this different ways to convince yourself that that's true. But we're not going to prove that rigorously. We're just going to take it as something that, if you think about it long enough, should seem reasonable. Okay, so we can write one case down here.
Why don't you start by checking the last character instead of the first?
Could do the first. It's the same thing. But we're going to work with substrings of m and n, and it's going to be easier to code if we chop off things from the end, because then our starting index is always 1, and all we have to do is change the ending index. But logically, it would work the same in either way. These should be square brackets because we're kind of in C. So if the mth letter of the first string is equal to the nth letter of the second string, we need to do the following. find the longest common subsequence of the shortened pair of strings. Right, that's this circled string and this circled string. And whatever the length of that longest subsequence is, add 1 to it, because we know we can tack on that last letter, and that'll give us our longest common subsequence of the original strings. And that's what we're going to return. So that's one case. If the last letters match, we can find the longest common subsequence. I changed my function name on you. Find the longest common subsequence of these shortened strings, add 1 to it. But there's another possibility. So in this case, these strings do not match in their last character. And now our situation is something like this. Okay, I'm going to claim that there's 2 possibilities here. So possibility 1, the longest common subsequence ends with whatever that symbol x is. It ends with the last character of string m. Okay, if that's the case, if the longest common subsequence of m and n ends with this character, then it does not end with this character, because this character is different from this one. So the common subsequence between m and n is also a common subsequence between m and a shortened version of n. Right? So if the common subsequence ends with x, it's a common subsequence also of this abbreviated version of n. Which means we could find that common subsequence as follows. Longest common subsequence of m, little m, n minus 1. So in this case, this will be the longest common subsequence of m and n. But there's another case. Longest common subsequence does not end with an x. May not end with a y either, right? But the 2 cases, it either ends with this character or it does not end with that character. And if it does not end with that character, then whatever the longest common subsequence is also a subsequence of the shortened version of m, because it doesn't end with x, right? So this longest subsequence of this is going to be the same as the longest subsequence of that. And in that case, if we were to find the longest common subsequence of m with m minus 1 letters and n with n letters, that would be the length of the longest subsequence of the original m and n. So here we simply return the maximum of this and this. And that's your whole function. So a lot of weird logic going on here, but not a lot of code. So to find the longest common subsequence of 2 strings, if the last characters match, find the longest common subsequence of the truncated strings and add 1. Otherwise, find the longest common subsequence when you truncate the second string, find the LCS. When you truncate the first string, return the larger of those 2. Because we don't know which case we're in, because we don't know what the LCS is, but we know that one of these will be the same as the longest common subsequence of the original strings. All right, so I coded this up the other night. There's a bit of housekeeping in here, but don't worry about the details too much. So LCS will take a string Okay, a character pointer, an integer number of characters, a character pointer, and an integer number of characters, and it will return the length of the longest common subsequence. And I'm not assuming my strings are null terminated in here, because I'm going to keep chopping things off the end. I don't want to keep putting in null terminators. So that's why I'm passing the length as well as the pointer to the first character. All right. The only thing I'm assuming is that LCS itself returns the length of the longest common subsequence. Okay, so what do? I'm clipping everything at 100 characters, just so I didn't have to go crazy with malloc. So your strings have to be 100 characters or less each. I prompt for the first string, I do an fgets to read it in. I prompt for the second string, do an fgets to read it in. And then I get rid of the new lines at the end, because I don't want new lines in here, because they get counted as part of the subsequence and it's confusing. So I'm getting rid of the new line that fgets includes in our strings. So now we've just got 2 strings of characters. And then I call LCS. I pass it strings S1 and S2 along with the number of characters, which I get from string length. And whatever it returns, I'm just going to print that out and say the longest common substring has length %d. So we'll go look at that in a minute in more detail, but let's run this thing. So we're looking on hello there, and this is fun, trying to find the longest common subsequence, and it's working. It's working really hard. So every time that I recursively call this LCS, I'm printing out what the strings are that I'm passing into it, trying to find the longest common subsequence of. And you can see it's doing a lot of work. And the longest common substring has a length of 2. I don't know if that's correct or not. Where are my strings? Hello there. And this is, I think I said cool. This is fun. So is there a common substring of length 2? Just TH. So it had to call LCS 75,823 times to do that. And it actually ran pretty quickly. We can just look at the tail of it. So most of that time that it spent was just doing the prints. But it still takes, you know, a good fraction of a second to do that. 75,000 recursive calls. So there's another test case. And this will tell us the longest common substring has a length of 3. This was our original pair of strings. So is there a common substring of length 3? What is it? SHA. SAJ, SAJ, there it is. Sag. So here's some longer strings. Yeah, but I got it by typing in, you know, in the middle of the keyboard, password generator. So string of length 13. And that had to recurse 89,000 times. So here's some longer strings. They're not that long. 32 characters each. This will run a long time.
What does tail do?
Just shows you the end of standard out in this case. So when LCS exits, then it'll know what the end of the output is. And it'll just show us the backside of that. But this ran for half an episode of what I was watching on Netflix. So it actually ran a little over 2 billion calls to LCS before it actually came back with an answer. So really expensive algorithm, right? So let's look at the rest of this code. So here's the longest common subsequence code itself. Base case, right? If either length is less than or equal to 0, there's no common substring, so just return a 0. That gets us out of our recursion, and we missed that in here, right? So got to have a base case. Because each time we do this, we're going to work with a shortened, at least one of our strings shortened, and the only way we get out of that is to notice that one of our strings has a length of 0. There can't be a common substring. So if the length is less than or equal to 0, no common substring, return a 0. This is where I echo the strings that we're working on. Remember, my arguments are not necessarily null terminated, so I made my own print routine that basically just prints out the first len A characters from A, the first len B from B, and it lets me just print out, working on such and such. All right, and then we have our two cases. So if the last character is the same, if A and B match in their last character, call LCS on a shortened version of A and a shortened version of B. In other words, take the first len A minus 1, len B minus 1 characters, find the longest common substring, add 1 to it, that's our return value. If the last characters differ, find the LCS when we truncate B by 1 character, find the LCS when we truncate A by 1 character, and return whichever is the longest substring. And that's it. That's all there is to the code. Very, very short function, but it'll happily run 2 billion times on a pair of strings 30-some characters long. All right. The other issue with this is we're not actually finding out what the common substring is. We're just finding the length. And all these things that we're doing, including PA5, finding the length, finding the maximum value, finding the maximum capacity is part of the problem. The other part of the problem is finding out what particular solution gives you that maximum. So what particular string of characters has this maximum length? So we need to keep track of some information. So here's my second version of LCS. And in this case, LCS is returning the actual substring instead of just its length. And my only assumption is that LCS returns a null terminated string so that I can use string length to find out how long it is. Otherwise, you need a structure with characters and length, and I was being lazy. So LCS will return a null terminated string, but nothing else is necessarily null terminated. So all the same setup as before. Read in a pair of strings, get rid of the new line, pass it to LCS, and this time I'm going to print out the longest common substring is whatever it is. And our code barely changes. So if either string has a length that's 0 or negative, I want to return an empty string. But instead of just returning quote, quote, I actually malloc 100 bytes. I set the first character to the null terminator, and I return that. This is the only malloc in the whole program. And it's kind of weird. The only time we have to actually allocate memory is when we want to return an empty string. That's a little goofy. If we don't do that, it's segfaults. Because the only time that we're adding anything to our strings is when we're getting back an LCS and we're tacking something onto the end of it. Right? And that starts when we've come down to a base case where our string returned a null. So we got to have some space for it to add on to. Don't worry about that. If it seems goofy, it should seem goofy. But let's just look at the guts of the code. So if the last character matches, I make a car pointer. I call LCS on the truncated strings. Whatever it returns, that's my car pointer, return RET. And then this is just some laziness in here. I wanted to tack a character onto the end of this string. And I know the string is null terminated, so I'm basically finding where the null terminator is, replacing that with the character I'm tacking on, and then putting another null terminator after that. And I'm doing it in a different order so that my string's always null terminated. So this puts a null terminator after the null terminator, and this replaces the current null terminator with the last character of A, or I could have used the last character of B. And then I return that as my longest common substring. If the last characters differ, call LCS with B truncated, call LCS with A truncated, and I take the strings that come back and I save those in ret1 and ret2. And then whichever one has a longer length, I return that corresponding string. And I think it's a little cool that these don't get malloc. Right? I'm just pointing to whatever LCS returns, but it works. So, and that's it, right? That's just my print routine for printing out things that aren't null terminated. So this LCS2, this is fun. Oh, hello there. Here, this is fun, and it'll chow through that. And I get bored easily. So common substring is TH. So there's our longer strings. There's the longest common substring. All right, so what do we do about the efficiency? This is where we want to start caching our results. Because if you look at this, right, and just stop it anywhere, JDH and J, JDH and J,
You save all the strings that have the
JDH
string
and
in it.
J. So let's save all the strings. Let's save the longest common subsequence for every pair of strings that we find the longest common subsequence of. And it's not like Fibonacci's where we just had a number n and we were trying to find Fibonacci of n. We've got two numbers now. We've got the length of the first string and the length of the second string. And we're trying to find out what the longest common substring is. So if our original string is hello there, that has length 10, and our second string is this is fun, and that has length 9. We're trying to find the longest common subsequence of this string and this string where the first string has length 10 and the second one has length 9. And it turns out all we need to know is what those lengths were, because the arguments, the first string and the second string, A and B, those never change. When we pass those to LCS the first time, they never change when they're passed to any of the subcalls to LCS. It's only these length variables that change. So to do this caching, it suffices to make a two-dimensional array called save. And I made it 100 by 100, and I initialized it to all null. And the idea is when we compute LCS of 10 comma 9, save bracket 10 bracket 9 will be whatever that longest common substring is. So now we're going to go through, we're going to do exactly the same thing we did before. We initialize our two-dimensional save array. And inside LCS, before we start doing any of our recursive business, we're going to check element length A, length B in our save array. If it's not null, we're just going to return whatever value we stored there. So this is a two-dimensional array of strings. And the entry at index ij is the longest common substring of the first I characters of A, the first J characters of B. So if that's not null, we've already saved something in there, we just return the value. Otherwise, we print out our message, we do our recursive business, and in each case, before we return, we save the value we're about to return in our array. So we malloc space for it, and then we copy the return value into that entry in our save array. And we do that up there, and we do that down here. Wow, I've got a big bug here, man. I didn't return ret. That's crazy that it worked. It only worked because ret was the last argument on the previous call, so it happened to be on top of the stack. That's a really annoying bug. All right, so that's added caching to our code. How much you want to bet I just broke it? So we'll go after our big long code. There you go. So there's the longest common substring of those two strings. Total number of calls, 497 as opposed to 2 billion. A little more efficient. All right, so that's just an illustration of a different illustration of longest common subsequence. But the general nature of that's common to like everything we're doing with dynamic programming. Okay, so I want to go back to knapsack problems. And we talked about the fractional problem, right, where you could pick oats and saffron and pistachios. And we talked about that being a greedy algorithm, right? So greedy in the sense that our goal overall is to maximize the value of stuff in our bag. And so the first thing is whatever we can do right now to maximize the value in our bag, which is to find the most valuable item, put as much of that in our bag as we can. And we're hoping that by doing that repeatedly, we're going to end up with the best maximum value overall. And if that works, then the greedy algorithm is valid. So that's fine for that setup. There's a different version of the knapsack problem, which is called the Zero-One Knapsack. And we're going to call it the Zero-One Unlimited Knapsack problem. And this is PA5. So the setup for the 0-1 problem is that you can't take pieces, you can't take a part of an item. You can't take a fractional amount of an item. You either take an item or you don't, 1 or 0, it's binary. And the unlimited part means that you have an infinite inventory of all possible items. But they're packages of oatmeal, for example. So you can take 1 package, 2 package, 100 packages, but you can't take half a package. And it's a very different problem, in particular because a greedy algorithm will not always work. So use case would be something like this. You win a shopping spree at Best Buy, and they say, okay, here's a shopping cart. Right, this cart will hold 100 pounds worth of stuff. You can stack it as tall as you want, but you can't exceed 100 pounds. And you can put as much of anything that you want in here. We have an infinite warehouse. Load this up to 100 pounds. Whatever you get in there, that's yours. So what do? I mean, you could get the 80-inch TV, but that's going to weigh like 50 pounds, so that uses half of your capacity. You could grab 2 of those. You could grab the 1 terabyte flash drive that's this big and costs $10,000, and you could load up on those. That's probably going to be worth an awful lot. Or maybe, you know, the really nice gaming laptop or whatever, right? So given an inventory of items, how much they weigh, how much they're worth, what's the best way to pick items to put into your bag or your shopping cart to maximize the value? That's the 0-1 unlimited knapsack problem. And that's what you're solving for PA5. So let's look at an example. So we're going to have a pricing table with the weight of an item the value of an item, and we'll put the name of the item here. So your first item weighs 1 pound and is worth $10, and that's a mouse. It's the wrist workout mouse that weighs a pound, so when you move it, it gives you good muscle development. Okay, item 2 weighs 2 pounds and costs $21, and that's a webcam. Remember when you had to buy a webcam because they didn't come built in? All right, item 3 weighs 5 pounds and is worth $56, and that's a hard drive. Probably like a 1 terabyte for 56 bucks. And item 4 weighs 7 pounds and costs $78, and that's a router. It's a big router. Yeah. All right, so you've got a certain capacity in your bag, and your goal is to figure out which items you should put into your bag. So one way to do this is to look at the value per pound. Right, one way to do it is just take the most expensive item first, but that's probably not your best approach. But let's look at value per pound. So your mouse is $10 per pound. Your webcam is $10.50 per pound. Your hard drive is $11.20 per pound, and your router is $11.14 per pound. So your hard drive is the most valuable per pound, right? This is what we would do if we were picking up oats and pistachios. Find the one that's most valuable. So let's say your capacity is 7. Well, if you start with the hard drive, so let's number these. So you take a hard drive, which costs $56 and weighs 5 pounds. Now you have 2 pounds left. You could take the webcam for $21, and that gives you a total of $77. Or you could take the hard drive for $56, and you could take 2 mice for $10 each, and that gives you $76. But it turns out if you take the router, that's worth $78. That gives you your best solution. So a pure greedy approach, which says let's take the thing that's most valuable per pound, is not going to get you an optimal solution. And taking the most expensive item is definitely not going to get you your most valuable solution, because suppose that our mouse was worth $40, right? Our most expensive item is the router, that's worth $78. But if we took 7 mice, that would be $280. So pure most expensive is not going to work. Most valuable is not going to work either. So greedy algorithms don't work in this case. So we need to do something different. And this is going to look a lot like the rod cutting problem. So let's make our pricing table. Let's number our items. Let's just number them 1, 2, 3, and so on up to item n. And the value of an item is going to be V1, V2, V3, up to Vn. And the weight of the item is going to be W1, W2, W3, up to Wn. So think of these as mathematical functions. Don't try to force them into C arrays, because I'm starting from 1 instead of 0. Think of them as a function that gives us the weight and value of the nth item. And now we want to make a function. Let's call it maxval. And it's going to take a single argument, which is the capacity of our bag. And it's going to return what the maximum value is we can get from a bag with that capacity. In reality, you got to pass the inventory lists, the weights and values and things like that. But bare bones, our function goal is to take in a capacity, return the maximum value. So let's write this function. Well, here's how we can think about this in terms of subproblems. Assuming that there's any items that will fit in our bag, right? They didn't give us a bag that only holds half a pound. Assuming there's any items that fit in our bag, we're going to have some first item that we put in our bag. Could be item 1, item 2, could be item n. But we're going to put some item in initially. And the order in which we put these items in makes no difference. In the end, we've just got a set of items. This is how much they weigh. This is how much they're worth. Right? The order is irrelevant. So let's imagine what happens if we put item 1 into our bag first. So item 1, if item 1 is placed in the bag, and the question is, now what's the maximum value of things we can have in our bag? So our best value is now, well, there's two pieces to this. First of all, we've got item 1 in our bag. So whatever the value of item 1 is, we've got at least that much that our bag's worth. But we probably have some space left in our bag, right? What's the new capacity of our bag? What's the remaining capacity of our bag after we put item 1 in? Capacity minus the weight of item 1. That's the capacity that's left. And if we can get any value out of that, we can add that to the cost of item 1. That's our total value. Okay, how do we find the maximum value from a bag with this capacity? Max val of that. So this expression is saying if we put item 1 in our bag, it's worth this much, and this is how much we can put in the remaining space in the bag. If item 2 is placed in the empty bag, so this is not after item 1, this is saying our first item is item 2, our best value is the value of item 2 plus whatever the maximum value is we can get from a bag whose capacity has been diminished by the weight of item 2. Cap minus W2. And in general, if item n is placed into our bag as the first item, our best value is the value of item 2 plus whatever the maximum value is we can get from a bag whose capacity has been diminished by the weight of item I. And since we know we're going to put some item in our bag to begin with, the absolute best value we can get from our original bag of capacity cap is either this, or this, or this, or whichever one of those cases has the largest value. So if we iterate over all the possible first items, I goes from 1 to n, and we calculate this and we record the largest value, that's our value of max val. That's the value we want to return. So let's code this. So let's return the largest possible value in a bag of capacity cap. So we'll iterate over all the possible items. And we'll say the value that we get by putting in item I is the value of I plus the maximum value of a bag with capacity diminished by the weight of I. And we want to find the best of those. So we'll say if the value from this item is bigger than the best we've seen so far, then record that as the new best. And when we're done, just return that best item, that best value. No, you're also going to want to know how you got there. Makes it more interesting. This is most of the guts of what you need to find the max val. There's a few details in here. So what's the first detail that we always come back to? Base case. Awesome. So what's the base case? Each time that we call max val, assuming our weights are not negative and they're not 0, this is going to be smaller than cap. So we keep trying to find the max val of smaller and smaller capacity bags, but at some point this may go negative or it may go 0. So we can throw in a base case here. If capacity is less than or equal to 0, we'll just say can't do. Max val is 0. There's one other edge case in here that we haven't accounted for. If it's equal, it's still going to be a value of 0. But think about our original pricing table. And suppose I ask you to find the maximum value of a bag of capacity 2. What's the answer supposed to be? Yeah, 2 mice, right? Okay, yeah, because that's a 40, I changed it. So 2 mice would be the answer there, right? Suppose we go back to the old value. So what's the max value for capacity 2? It's a webcam, $21, right? But this loop, the way we've written it, when I is equal to 3, it would take the value of item 3, which is $56, and add the max val of a bag with negative capacity, which will be 0. It's going to say, well, if I start with item 3, I get $56. That's going to be better than the 21. And the 78 is going to be even better. So what's going wrong in here is that we're potentially adding items that don't fit in our bag at all. Right? So before we can say what happens if we start with item I, we have to make sure item I actually fits in our bag. So you need to surround this with one more condition. If weight of I is less than or equal to the capacity, then you can do all of this business. Otherwise, you start getting really funny results. All right. So with that, this will give you the maximum value. And it will do it very inefficiently. Right? Because suppose we have our original pricing table. So weight and value. And let's say our first item weighs 3 pounds and our next item weighs 5 and 6 and 10. And we want to find the maximum value from a bag of capacity 20. Well, we're going to say, let's put in our first item. And that leaves us with 17 pounds, so we'll need to find max val of 17. Or we'll put in our second item and find max val of 15. Or our third and max val 14, or our fourth and find max val 10. And to find max val 17, we'll consider putting in the first item and having 14 pounds left, or the second item with 12, or the third with 11, or the fourth with 7. And to find max val 15, we'll do the same thing. And at each level of our tree, we're getting 4 times as many nodes, right? So for an inventory of 4 items, the number of spots in here is going to be roughly 4 to the n, where n is however many times it takes us to get down to a capacity of 0. So this is like super exponential. It's a technical term. If you have n items in your inventory and your smallest item will fit m times into your original bag, it's something like order n to the m. It's really, really bad. Okay, so we're going to have to do some caching of results here. So the other detail is that this is just giving us the maximum value. It's not telling us how to get that maximum value, right? So we're going to actually want to record the inventory that gives us this particular value. And we'll need to embellish our code accordingly. But it's really not that big of a change. We want max val, instead of returning an integer, to return an inventory. So you probably want something like a structure that has a list of how many of each item you want and what the value is from that corresponding inventory. Now, how can you do that? Well, we already have our items. Right, and they're indexed in some way. So you could just make an array called inventory, and entry 1 is the number of item 1, entry 2 is the number of item 2, and so on. And so if your solution was to have 2 webcams, 3 hard drives, and 5 routers, and 0 mice, right, then inventory You could just store 0, 2, 3, and 5. Make the index 0 instead of 1, et cetera, right? But the idea is to record a particular inventory, you just need to know how much of each item you have. And a simple array of integers will do that. So now, our maxVal function returns that array along with the value of that arrangement. And if we find the maximum value from this diminished capacity, we've got an inventory that gives us that max value. Just adjust that inventory by adding one more of item I. So you just increment the ith element in your inventory array. That gives you the inventory for this particular value. And you have to save that along with the actual value. And if the value is bigger than what you've seen so far, save the new best value and also save the new best inventory that corresponds to it. And when you're done, instead of just returning the number, return that saved inventory. And if you do that just right, it's pretty painless. But it's something to think about ahead of time. All right, so let's take 5 minutes, and then let's talk about PA5. We'll go through the assignment. I'll show you some sample execution of it. We'll talk about the group aspect of it, and so on and so forth.